Okay, now perhaps I will also want to make sure, okay, for the schedule or final, because I think in last discussion I've mentioned that we will have on Friday, 10th of June. Is that correct? I have mentioned that in the discussion, right? Just to make sure later we can have more another discussion if you want to change the schedule. Okay, I can adjust the schedule with your other courses. Okay. Okay. So if you haven't scanned the QR code, you may scan the QR code. I will give you a few minutes, okay, before we start our course. Today I will just continue the last chapter. Okay. So chapter 7, finishing chapter 7, and then chapter 8. Chapter 8 will be consist only two sections, 8.1 and 8.2, and I think that is sufficient for our calculus. So next Tuesday, the class will be about review. If you have other schedule for final exams preparation for other course, you may skip my classes. That's okay for next Tuesday. You can just watch the video, okay, and the attendance I will not count it on Tuesday. So you can come, or if you want to skip, you may skip the class. Okay, I think we can start. Okay, I believe we are having uh, discussions on the improper integral. Okay, and we have. Let me just review a little bit of what we are having in 7.7 and 7.8, the improper integral. So improper integral means that uh, we will have first we will have the integrants or the interval for the integrations. We have infinite interval. We call it infinite interval. Okay, that's the first case for improper integral. So that's why if we take it into our regular integrations, we are not really getting the finite result, right? Because of the infinite interval. So we need to make this integral. We need to add the limit. Okay, we need to add the limit. So then we can limit the interval. Okay, when the limit approaching infinity. Okay, for the interval. That's the first case. So you can have the infinite interval. The second case that you might have is uh, the discontinuity integrand. Okay, so you have a discontinuum. Okay, which means you will have an asymptote. Okay, so what will happen if you are having a function and you have some asymptote in between, okay, or maybe at the end or at the beginning you have the asymptote. What will happen? So again, similarly, you will have a limit, okay, and you need to make sure the limit goes through approaching from the left or from the right. Depends on the conditions, but you need to apply limit, okay. But basically, what you are going to do, the techniques, all the calculations, all will be the same techniques. Okay, so first, maybe you can set up the integral. You take as indefinite integral, and then at the end you can put the interval, or you can put the calculation for the improper. Okay, so let me give you a question. A questions. Okay, an example. So let me give you an example first on how we are going to analyze our questions. So first is let me check. So you have integrations from -1 to 0. Okay. You can also try. Okay, you can also try to check whether you can solve this problem or not. It takes time, several process inside. But first, okay, because we are now in the improper integral, so we need to check whether the interval is defined or not, or whether is there any discontinuity, right? So first, check through discontinuity, and we know that the problem is 0, right? The problem is this 0. Now, what will happen? If you put 0, it will be undefined, okay? So if we let our functions as e at x equals 0, the function is undefined, right? Or we know that probably there will be some discontinuity at 0. Discontinue or just discontinuity. Okay. So first, we can say that we can take the limit of some variable, let's say t, approaching to 0 from the left, right? So we will have this is -1, 0, so it's going to be here, right? Okay. And integrations from -1 to t. And this will be e 1 over x divided by x cubed and then dx. Okay, now the problem is how to solve the integral itself, right? So not only we need to think the improper integral, but we need to think how to solve the integrations itself. Okay. So what I can suggest to you is, if you don't want to make confusion in the process, maybe we take the integral, okay, just take the indefinite integral, take this, and we are going to evaluate this first. So if we evaluate this, okay, this integration first. So I think we can try to apply or utilize some concept that we have learned in our study to solve this. Any idea how to solve it, or anything that you can make from this? Can you try? Let me just give you a few minutes to try. I give you examples that I think it's quite take times for the technique itself, and it's also improper integral. So I need to give you all this aspects so that we can cover many things, okay, at the same time. Okay. Okay, now, if we are going to take the substitution, for example, if you are going to take substitution, use substitution. Can we do something? let's say we are going to have substitutions on 1 over x. Okay. If we derive this will be becoming negative 1 over x squared, right? And then this will be dx. Okay. If we try to make out as in our equation, so let's substitute. So e with power of u, and then x cubed, and dx will be negative, okay, negative x squared du. If we take cancellations for this one, this will be negative eu, and we will still have 1 over x du. And remember, we are having 1 over x as u, so this is, we can exchange this 1 over x with u, e, u, negative, and du. Okay. I hope everyone clear in my methods here. Okay, now I believe rather than these structures, these fractions, this one is easy to follow, right? Easy to integrate. Okay, I think we can integrate easily through integration by parts, right? So we can take this as u, and this is dv, or we could take the di method, as I mentioned in the previous lectures for integration by parts. So now it's, you have u, and this is e u, and you have 1, 0, plus, negative, plus. This is the same in all integrations, right? And we can cross multiply. So we will have negative, because it's negative from here, u e u minus e u, or eu minus u eu. Okay, and then plus c if you want, or maybe change u into the 1 over x if you would like. Okay. Well, if you just make it into u is also fine, because this is not finished yet. This is just part of the techniques that we are going to utilize to solve the integral. Okay, now we are looking back into our improper. Okay, so we go back to here. Okay, we go back to this improper, and then we are going to solve these integrations through the limit that we are applied here. Okay, so we can write a limit as t approaching 0. Let me write the fractions. Okay. Okay, let me just take the answer from this one. Okay, let's take this eu and negative u e with power of u. Now, before doing that, let's take this u as 1 over x. Okay, so as x is negative 1, then u is negative 1, right? As x is t, right? u will be 1 over t. Okay, I will change to du so that we can have a simple equation rather than the dx. Okay. So this will be, turns out to be e u minus u e u. Or maybe let me write the integral to make it more complete. This is the negative 1, 1 over t, okay? And this will be negative u e u du, and this will be equal to limit, and we can directly write eu minus u eu from negative 1 to 1 over t. Okay, now slowly we are going to input the result. Okay, now we are going to input into the equations. That's the first one. Second one, we have e negative 1 plus e negative 1, right? Okay. Now we have 2, so limit the so this will be negative 2 e negative 1. We'll move into the front plus this will be e 1 over t 1 minus 1 over t. Okay. Okay. Now to help our calculations, I think this 1 over t we can make into some sort of another substitutions. So 1 over t, we are going to substitute with s. So when t is going to be approaching 0, okay, then s will be approaching negative infinity, right? Okay. It's supposed to be like this, right? So it's going to be going there, right? Okay. And now we still write, we can write with s approaching negative infinity. This will be negative 2 over e. Okay, we write this negative 2 e negative 1. And then let me change the structure, the positive negative. So I will write the positive in the front of minus e s and 1 1 over t in the front. So I will write this will be should be 1 over t minus 1. Okay, just changing these two positions. So we can write this 1 over t become s minus 1. Okay. And then we can write, since 2 over e is just a constant, and we can just put here, and we have limit s approaching negative infinity, okay, and we have s minus 1 over, let's say this is e with power of negative s, right? Okay. Now take it slowly. Okay, take it slowly. if we want to take the limit from here, if we check the limit, we will have infinite over infinite, right? So we can do L'Hopital rule, okay? So we are having the L'Hopital rule. So this will be 1, and this will be negative E, negative S. Let me mark this with LH so you know that this is a L'Hopital rule, okay? Okay. Now this E power negative S, okay, and having negative, if we put infinity, this will be resulting 0, right? A 0. 1 over infinite, right? This will be 1 over infinite. So this whole part here becomes 0, okay? So then we can finally get the final result as negative 2 over e. It's a converge. The improper integral is a converge. Okay, converge to negative 2 over e. So we can write the sorry. We can write these equations as negative 2 over e, or converge to this point, this number. Okay. Okay, now any questions? Okay, I hope it doesn't get confusing. Okay, so first is to solve the integral first. Okay, to solve through some techniques, and the other part is the improper one. Okay, using the limit. So you have two different techniques. Right? The first technique is the technique of integrations. You can use substitution, integration by parts, or any other techniques that you can think. The other part is limit. So your limit knowledge on chapter 2 and also chapter 6 on the L'Hopital rule, it will be applied. Okay, it will be applied here. Okay. Okay, let me give you a few minutes to take notes. Yeah, any question?
A bit complicated, Professor, but it's okay.
Yeah, it's complicated because I want to show you the whole thing through this one example. I think the complicated one is in for the limit. I believe this part is quite complicated. Okay, this part here. You need to be careful. Okay, careful when you follow up the limit. Okay. First, if you encounter limit, check the limit first. Okay. Whenever you find the limit 0 over 0 or infinite over infinite, you can do L'Hopital rule. Okay. Okay, wait for a moment. Okay, so we can take a few minutes to at least to process all the methods here. Okay. Okay, I think we can move on. Or do you still have any trouble in this part? Uh, so maybe a little bit a review on what we have. Okay. So first, this is the question. Okay. And we know that from the question, this is going to be having the discontinuity, which means that we are going to solve through the improper integral, right? Okay. Now, before we solve through the improper one, we can take time to solve the integral itself, okay, the technique of integration, okay. And we get this result, okay, this part here, okay, this one, we get this as our result. Well, you can just using this one and change x with t for this one, okay? But I want to make it more simpler, so I take u, okay, so that I can make it into this substitution here. So probably will be better rather than 1 over something in this equation, okay. Now, after we get this result, we're going to put into our improper integral, okay. We're going to put into improper integral, and after we check the interval, okay, we check the interval, we changing all to u, and then we take this as our solutions, okay. And then this part, okay, the second part is the limit, okay, the limit part. So the first part is the integral, okay, the technique of integrations. The second part is the limit, okay. So it takes time to check the limit, okay. So we solve first, take some simplification, some algebra here and there. You get this, okay. This is already a constant, so don't worry about this part. What we are worried about is this part, okay. Okay, my suggestions, every time you have limit and you have 1 over something in this power or any in here, you may change the perspective through this limit here. Okay, so this limit here, we can change the perspective with other variable. Okay, so we take the 1 over t as our s, so that when we have t equal or t is approaching 0, we will get negative infinity, okay? How I know it's negative? It's from this 1 over x functions, okay? When you have the going to be the negative, it will be infinite, okay? Going to be infinitely large in a negative way. And then after that, we can check with the s in our equations, okay? And then it takes time. Okay, remember this is I believe it's on your indeterminate forms. Okay, indeterminate forms. So it takes time. Check the L'Hopital, and then you will have the derivative. Okay, derive this with respect to s. You get 1. You get this negative e, negative s, okay. And check through this infinity. This will be resulting infinity, right? This one is infinity. So 1 over infinity in limit terms is equal to 0. So we can directly say that the answer is this, okay? Or we can say the improper integral is converge, okay? Okay, that's what we have. Okay, I think we can move on. Okay, move on to the next section, which is the comparison theorem. Okay, comparison theorem. Okay, we'll move to the next one. Okay, let me check. I think this one. So comparison theorem. So suppose we have f and g are our functions that is continuous. We know that f is, so first is the definition. So f is greater equal g and greater equal 0 for x greater equal a. Okay. And then we have two conclusions. If the first one, if this f, okay, if this is converge, since f is greater than g, then for sure, okay, then G is also converged, right? Because it's smaller than the F. So this G also converge. Okay. I don't think the first one is any problem with the first one, right? But the second one, okay, the second one. Now we look on the G itself, okay? So if G diverge, okay, if this is diverge, then F also diverge, okay? And again, we take f of x greater g of x, okay? If we say, oh, wait, it's supposed to be g, sorry. Okay, now, if f of x diverge, let's say this is a dx, the improper integral diverge, what will happen with g? We cannot make a conclusion because since f is greater and g is smaller, f may diverge, but g, it can converge, it can diverge. Okay? So this comparison theorem doesn't happen. Okay, if this case happen. Okay, so the case only happen if you have these two cases. Okay, and how we are going to apply? We are going to apply based on this comparison f and g. Okay. So if you have any unknown improper integral and you want to solve or you want to find whether the integral is converge or diverge without exactly knowing if converge how much it's converge the numbers. If you don't want to know about the numbers, you can use the theorem. Okay, you can use the comparison theorem. Okay, so comparison theorem is just comparing and just making confirmation that okay, this is converge, this is diverge. But if it is asking how much is it converge, it doesn't really say anything about that. It's just saying converge and diverge. Okay, I think we can check the example and make some cases to see how we are going to use this converge diverge situation. Okay. Maybe giving you time for writing the comparison theorem. Okay, let me go to example. So the question is just asking whether this improper integral converge or diverge. Okay. Okay, you can tell me whether it's converge or diverge. You can message through the chat box. Okay. Okay, is it converge? Okay, converge. Good. Okay, good. Okay, I believe this is the tips for you. Okay, if you have this kind of questions, and the question is doesn't really need to compute, okay, or to calculate. Okay. Then what you're going to do is take, for example, these fractions. Take this variable. Okay, since it's just plus one, so it doesn't really matter. Okay, so we take this x over x cubed, and we can say that this is 1 over x squared, right? It's it's half the same weight as the 1 over x squared, the same value. So if we are using this 1 over x squared as a comparison, I think it's quite valid. Okay, so since this 1 over x squared is going to be larger than the x, or let's say, x cubed plus 1, right? Because you have plus 1, so the bigger the denominator, the smaller the value will be, right? Okay. So this is, I think we can make sure, okay, this is true, that this is greater or greater equal. Then we know that if we take the integral of the improper integral of 1 over x squared dx, this will be resulting a converged one, right? Because of the p series, right? The p series. If you remember what we had last discussion, this is converge, right? Converge when p is greater than 1, right? Okay. And another tips for you. In the exam, I may ask to analyze p for this kind of functions, but the interval may be a little bit different. So you need to break down another p series with our p task with different interval. Okay, but I hope everyone can review later, okay, how to break down this and making how to know that the integral will converge or diverge through this p. Okay. Okay. Nevertheless, the integral is converged for this one, and since 1 over x squared greater x plus 1, and this integration is converged, then, okay, by comparison theorem, this x cubed plus 1 dx also converge. Okay. I hope everyone agree with this method, and I think it's quite easy to follow, okay, for the introductions, okay, for the comparison theorem. Okay, let me give you another example, at least two more examples to see how we can practice. Okay. Okay, I will wait for a few minutes. Okay, I will wait for 1 minute for you to take notes, and we can move to other examples. Or if you have any questions, you can ask. You can ask through chat box, or you can ask directly. And maybe at the last 10 or 15 minutes later, we'll maybe explain a little bit on uh, the schedule, the finals, okay, some little bit with details, okay, and also the quiz, okay. And hopefully the quiz is by this weekend, okay, weekend, or yeah, weekend. I will post. Maybe you can check for 3-4 days. We have some durations for checking. Okay. Now, next questions. I have two questions. First one is 1 plus sine squared x. This, and the other one is okay. So we have two questions. And this question is just asking whether it's converge or diverge. So let's say this is number 2, this is number 3. The question is just converge or diverge. Okay. You may think, you may check with some other function that you can compare. I believe I will give you easy comparison. Okay, number 2, is it converge or diverge for number 2? You can write in the chat box, converge or diverge. Number 2, converge or diverge. Number 3, converge or diverge. Okay, any idea? What about number 2? Is it converge? Any idea? Okay, now probably the sine squared makes a little bit confusion. But remember, sine or even sine squared, let me write sine x have a minimum and maximum value of -1 and 1, right? Okay, so sine squared is supposed to have 0 to 1. So if we plus with sine squared, of course it should have a positive number, okay? In any positive number that it might have, right? From 0 to 1. Okay, so we can consider the integral from 1 to infinity of 1 over square root of x dx. Okay, consider this. And this, if we remember from the previous sections, which has the x with p greater 1, then it will be converge. And p less equal 1, this will be diverge, right? Now we have x with power of half. It's less than 1, right? So this will be a diverge. Diverge in the conclusion, okay? So since 1 plus sine squared x, we need to prove first what's the relation with this. And of course, because like I said before, it's plus this sine squared, okay? Of course, it should be greater, okay? It should be greater or equal at least, okay? But we can say it's greater. And then the and the integrations is diverge as a conclusion. This also diverge by comparison theorem. Okay. Okay, I hope the structure is clear. Okay. So first, you need to find a function that you can compare. Okay. Check the result, the converge or diverge, and then you can make a conclusion. Oh, my video is not on. Okay. All right. Now the third question. The third question is a secant squared. Okay. Now it has the same trigonometric, similar trigonometric, and secant is also we can have -1, 1, and it's squared, so it's supposed to be 0 and 1. So let's say it's a positive number, right? So the same thing what we have in the previous case, with the difference, it's 1 over x squared of x, right? So let's consider this. Consider this function. Consider this function. So first, we need to consider to find the integral of these functions first. So we need to consider to integrate this. Okay. Now, of course, it is different from what we have in the p task. It's from 1 to infinity. So we need to break down this task first. Okay. So we need to break down the integrations from 0 to 1 for 1 over x with power of p dx. So we need to find this first, please. Well, we can start when p is equal 1. Okay, so we can have 1 over x dx. So we can have a limit as t approaching 0 from the right. And then we can change 0 for t. And we can take this, make it ln. Okay, ln t to 1. And the result is it's a divergent. Okay, it's a diverge, right? Divergent because of L and 0. If you put 0 here, it will be infinity, right? So we call this divergent. Now we check for the general terms for P. So we check for 1 over x P dx. So we are going to take the limit, okay? Take the limit. And then change this. Okay. And then solve the limit through the power rule for the integral. We have 1 over 1 minus p, right? And then we have t 1 minus p over 1 minus p. So I will factorize this, and let me write here a bit left. And this will be limit, or let me write limit with red color. So this will be 1 minus t, 1 minus p, okay? Basically, just to plug in 1 and t to x. Okay, now to make our analysis more approachable, now let's take the t with power 1 minus p as 1 over t p minus 1, so we can analyze the p easier. If we have p positive or greater 1, okay, so we have p minus 1 positive, okay, so 1 over t p minus 1. What will happen if this p minus 1 is positive? Okay. When t is approaching 0, this will goes to infinity, right? Or we call this as a divergent. Agree, right? What will happen if p less than 1? So we will have a negative and a p minus 1. So when we have t, p minus 1, this will result in infinity, right? In this part, we will have, if this is negative, okay, so t will have a negative here, so we have 1 over t, okay, 1 over 1 over t, so 1 over 0, okay, so or 1 over infinite, okay, 1 over infinite. So this will be 0. And we may also look on that this is a convergent. Okay. And now we are going to apply into our improper integral. So we can write that from 0 to 1, x 3 over 2, right? So this is p is greater 1, which is divergent, okay? Which is divergent. So this will be a divergent. And by looking at the functions, clearly that this is greater, right? So we can say that by this is or also diverge by comparison theorem. Okay. Okay, any questions? Okay. Now after this part, we will move to another chapter, which is chapter 8. I plan to finish at least the primary content. Okay, the primary content. And for additional one that we will have, I believe, just a review and exercise. Okay. So I will take my time to finish all subject by today's lecture. Okay. Okay. Let me move to the new page, and we are going to have a new chapter. So chapter 8. This will be just two main idea for this chapter 8: arc length and the surface area, or we call surface area revolution. So what is arc length? Arc length, in our definition, or in our case, this is supposed to be, let's say we have a random function like this. Okay? We want to measure the length from this part, from A to B. So measuring how long the function is. That is our idea, our objective. Okay, our objective. Well, first, if you want to measure, okay, of course, if we are having this random functions and it's not a straight line, it's a curve, it will be a very difficult task, right? But remember, we have tools in calculus. Okay? The first thing is you need to remember that we already make some topics about the linear approximations, right? Remember the linear approximation. What this linear approximation tell us? Okay. If we have, for example, if I take line, maybe in this point here, if I say this is point B, if I take line and make a tangent line, okay, maybe a little bit straight like that. Of course, if we are moving away from P, let's say we are moving away from P, we have a distance, right? We have a gap. Okay, we have a gap. But if we look on the point nearby, the point that near, maybe here, maybe around this one. Okay, maybe let me make a circle around that P. Maybe around this P, we can see that it's really close, and sometimes we are not sure that if we can differentiate the line and the curve, right? The straight line or the curve. Now, how about if we can make some slicing? We cut, okay? So we cut this, we cut cut like we do the integral. We cut all this. We cut and cut, and then we take the line between. Perhaps we can make some approximation, and that is the method, okay, for the arc length. The first sessions for the arc length is we are going to take our times to see this analysis. So let's look at this, and let's say we have a random function f of x, okay? And we have a point A, point B as the end interval, and let's say we have each point for each slices p0, p1, p2 up until pn, and at the middle, let's say we have a samplings pi and pi minus 1. We can say it can be in anywhere, okay, because it has, let's say, a lot of n, okay, maybe thousands, millions, I'm not sure, but it's a lot. Let's say it's a lot, okay? So we can simply say that the length of the total length for these functions is limit when n is approaching infinity, okay, of our sum, the distance between pi minus 1 and pi, okay, which means that this Riemann sum telling you that we are going to look this, okay, and then we plus with this plus all over the length, okay, all over the functions, okay? We are going to plus all the distance, okay? So we slice the point and we are going to add all of them, okay? That's what we are going to do. Now first, to break down the distance formula, we are going to see that the delta y, okay, is equal with the difference between yi minus yi minus 1, right? We have the distance. And the distance formula is given by using the triangle Pythagorean theorem. So we can simplify. This becomes a delta x and delta y. Let's say squared like that. Okay. And we are going to also to apply the mean value theorem that stated that if we have f, we will have the tangent. So this is where the tangent is coming. But don't worry about this part, okay? I will have a much more intuitive method to be explored. Okay? So this is, we can say, we can have our linear equation for our tangent, and we can say that this is equal to this, which means that we can exchange this with our f prime. So we can write down minus, so this is the distance. So we can write down this becomes okay, and then we can take out the delta x. So we can write 1 plus f prime xi, this is squared, and this is delta x. Okay. Now from the definitions, we are going to use the definitions that is stating the limit as n approaching infinity. That this will resulting in the Riemann of our 1 plus f prime xi sampling and then squared delta x. And by definition, with limit and Riemann sum, we can simply say that this is integration from a to b square root 1 plus f prime x squared dx. So this is becoming the arc length formula. Notice that you may change to dy and change to f prime y, or maybe if you want to write in more clear that this is dy dx, you can also write as the dy dx x, or you can exchange the dx over dy for dy. Okay, it depends on you. Okay, which one you are going to observe. But usually just dx, I think it's fine. Okay, another way to look this formula, okay, rather than using the distance formula and taking the Riemann sum, we can take more intuitive, okay, and since we already know the integral, we already know the first half of the calculus, right? So we may take, let me check whether we have, okay, we may take this, okay. So let's say we have this, okay. So let's say we can imagine the triangle being so small, and we can take the d as really small. The dx, dy, ds is really small. Okay. What we are going to do is we are just taking the ds squared is equal dx squared is equal dy squared. Okay. And sometimes they are using L, sometimes they're using S, but that is the arc length. Okay. Maybe we are using L. Okay. Let me change to DL to make sure that we are on the same page. So maybe DL with big L like this, and we take the square root, right? And then we somehow make this equation, and we take this and make some differentials. You can write like that, right? And then we can make that this will be 1 plus dy over dx squared dx. Okay. And then we integrate that L is a to b 1 plus dy over dx or squared and dx. Okay. This is more intuitive approach that you can always remember, but the definitions through calculus is this one. Okay, through this distance. Okay, this is the official definitions. This is the more intuitive when you are just looking out. If you forget the formula, okay. If you forget the formula, you can go back to this Pythagorean. Okay. Okay. So another thing on this arc length is we can observe this arc length. So we have when we have, for example, we have this is our f of x, okay? Or let's say this is our curve, let's say this is our curve. Okay. We may analyze the arc length and measuring maybe just a segment. Okay. So maybe measuring just this red line here. Okay, let's say this is from A to some x. Okay. And we may take this segment as a function. And we can have our arc length as a function. We call this the arc length function. We can also observe the arc length as a function. Okay. Let me write in the new page. Maybe let me just write here to make it. I think it's just some additional notes. Okay, so arc length function. If C has equations y equal f of x and A less x less b, let s x, okay, a distance, be a distance along C from, let's say P0, let's say at some certain point A, f of A, let's say this is P0, to Q. Q is some x, f of x, okay, this one, Q. Then our s of x is integration from A to x, just as using the same arc length formula, but using another variable inside. Let's say we have a variable t, okay, just to make differentiation with the x as our in our arc length function. So we are using variable t. And this is what we call the arc length functions. Okay, and that's the arc length. So the important thing is looking at this formula here. Okay, and I don't think if you want to check how it looks or how it's going to be proven using this one, okay, using this limit. But if you want just how we get the structure of the formula, you can use the Pythagorean. Okay, Pythagorean, draw a triangle, take the x, the y, and the l, and take the dl as your subject, and you will get that this is our formulations. Okay. Okay. I want to give you an example, but I think I will just go through the sections 8.2 for area of surface, and we can have more discussions later on, right? I have uploaded the additional video, okay, for chapter 7 and 6, maybe, if I'm not mistaken. And maybe next week I will add maybe one more videos for you to watch and practice about the chapter 8, okay, and maybe some of chapter 7, okay, so that you can have more ideas on how to prepare for your finals. Perhaps any question on the arc length. Okay. I think arc length, just taking the left bottom part, okay, for the equation, I believe that should be sufficient for most of the cases. Okay. Okay, I will move to the next sections and giving you a final part on chapter 8. Okay. Okay, chapter 8. The last part is 8.2, the area of surface or surface area revolution. So area of surface revolution. Does it mean? Okay. First is we need to recall what we have in the chapter 6. We have let's say a functions. Okay, we have a functions. We are rotating the function through this x-axis, and we are going to have our volume, right? Our volume like that. Now, the question is, we know the volume. Okay, we know the volume, the volume of the solid of revolution. But the question is, how about the surface? Okay, the surface that is revolving around the solid. Can we identify the surface? Okay. That's the question. So first, before we set up definition and formulations for the surface area, let's take some geometric examples. Okay? Let's say from here. Okay, let me take this. Okay, let me take this cylinder. Okay, let me take cylinder, and then take the cone, because this will be the main part of our surface area. Now, if we break down this cylinder, okay, if we cut open, then we are going to see that, oh, we have the area is 2 pi r h, right? Area is 2 pi r h. Okay, that's our surface area. And if we cut open the cone, we cut this, and we are going to have, okay, this circumference become this 2 pi r circumference, right? And what is the area for this one? We call this area as a sector. It's like a piece of pizza, right? A piece of pizza. So this is a sector. The area of sector depends on the theta divided by the full circle, multiply with the pi, and then the radius. The radius here is L. Okay, so L squared. Okay, so A is half theta L squared. Or if we would like to see the relation for the circumference, so circumference has 2 pi r, okay, is equal to L theta, the arc of the circle, right? So this line here, this line, the circumference here, is actually, we can relate to radius. So if we have a circle, if we have a radius r and then theta, this one here is r theta. Okay. At our case, we are having L and theta. So 2 pi r, the r is r within this one different circle, right? So we are going to have the theta is, or the L is 2 pi r over theta, or maybe just 2 pi r, and then we can just change this L theta here. So A will be half, and then 2 pi r, and then L, or we have pi R, and L, okay, from this cone. Okay. Why cone becomes important? Because most of the case we will have, okay, when we have the function that is rotated, we are going to define these functions as pieces of a cone that is slices. Okay? So imagine that if we take this and imagine that it has a cone like that, okay, and it's cone like this also, and okay. So imagine we have a cone we can slice. That slicing we were going to use for analyze our structure, okay, for the surface, and we call this structure as a frustum. Okay. Let me check if I have, yeah, here. This is the frustum. So we are going to use this frustum to formalize the surface area. Okay. Okay, let's say we have, okay, instead of just L, okay, we're having a cut. Okay, so we have cut. So the top one is removed. Okay, it's removed, and we now have two radius, R1 and R2, L and L1. Okay. Now, if we calculate the full cone with the top, okay, the full cone, we have pi R2 L1 plus L, right? Okay, area, the area of full cone from this pi RL. Okay, so we apply into our first term. Okay, now the second, area of the small cone, which means the small one is this one. Okay, this will be pi R1 and L1. Okay, so the part that is on the bottom is the big one minus the small one, right? Okay, so we can make a subtraction. So pi R2 L1 plus L minus pi R1 L1. Okay, so pi R2 L1 plus pi R2 L minus pi R1 L1. Okay, we make some groupings. So pi L1 R2 minus R1 and then plus pi R2L. Okay, and now looking at the triangle of this triangle, by the congruency of the triangle, you can say that L1 divided by R1 is equal with L1 plus L divided by R2. Or we can simplify it, become and we can also simplify and write as R1 L1 plus R1 L. So we can have these relations of R1 L is equal L1 R2 minus R1. Okay. Now from here, we can see that R2 minus R1 is this one, right? So we can exchange into R1L. Okay. So let's make some, let R be average radius. So R is half R1 plus R2, average radius. So 2R is R1 plus R2. Okay, and then we solve the equation here. So R2 minus R1 is Or if we take this R2 minus R1 is R1L over L1. So L1 will cancel, so this will be pi R1L and then plus pi R2L, or we can have pi, and this will be pi L R1 plus R2. And based on what we have in our definitions, R1 plus R2 are 2R. So area will be 2 pi RL. Okay. What is R? What is L? We can construct our schematics, but what we have is actually if we have a function like that, and if we rotate through here, okay, this will be the R, and this will be the L. Okay, so L is arc length, and R is the radius. Okay. Okay, let me just wait for you for processing all this chapter 8.1 and point 2. And the proofing is practically similar to what we have in arc length, so I just skip that one and just making formulations throughout this frustum surface area. Okay. Okay, maybe any questions first? Any questions? Okay, let me go to the next page to make some conclusions. Okay, I hope everything is okay. So conclusions is we have this, okay, and we have this. Okay, let me just take it into here, okay, and then write some notes. Okay, now the surface of revolutions. Okay, as I mentioned, this will be very similar to what we have in the arc length. So we are going to have a distance formula for L. So we have a distance cutting all the pieces here, but we are making into our 2 pi RL. Okay, so this will be the approach is going to be using the this average value and the distance of B. But I will not just proving this to you. I will just write the conclusions. Okay. The conclusion from here is we will have the surface area. The surface area is two pi f of x, okay, and the square root 1 plus f prime x squared dx. And how to determine which one is which? Remember that the base of the formula is 2 pi r L. Okay. This r is the radius. Okay, radius means that if this is a function, then this is the height of the functions, right? This is the function itself. So the radius is our function. Okay. So that's why the radius is this one, and L is the sides. Okay. So if you have L here, then L will be here. But since it's the dl, okay, then it will be very, very small. And since it's integral, we are going to plus all the dl on this function. And that's why we have the integral. And that's why we have this as a component of our L. Okay? Now, what is the important things that you are going to be aware? Okay, you need to be aware of. First is we need to see the rotations. Okay. For example, if you rotate like the usual case at the beginning, I told you that this will be our radius, right? Our radius is y, or function of x, right? We can say it's function of x. So we could write 2 pi y ds. ds is for the dl. Okay, sometimes they use s, sometimes they use l. It's still the arc length. Okay. Its rotation above x-axis. If you rotate through y-axis, the radius becomes x. Okay? Or sometimes it's become a function of y, probably, right? Function of y, g of y. And then the rest, this is the s, the same arc length. And how to measure arc length? You can use the x, you can use dy. It's okay. But you can also consider what terms you have in radius. You can consider which arc length you are going to select, dx or dy. Okay. So that's all the primary content for chapter 8. Okay. Chapter 8 still has 8.3, 8.4, but I think it's not really that important. I believe the important point in the chapter 8 is the arc length and the surface revolution. Okay. So maybe to make you remember that arc length can be, so ds can be written as 1 plus dy over dx squared dx or ds. Both of them can be used dy. Yeah, I would like to give you an additional practice example, but I think I will just focus on our finals preparation for today's, and maybe for some announcement. Okay. So let me open pollings, and to make sure that we are agree which day we are going to have a final. Okay, let me make a polling. If you have any other suggestions, please let me know. I will open the polling. Please check your system. We have 11 students, so I hope everyone can vote. Okay. The default, I think, if you last time is 10th of June, but if you want to make it early, I think it's also fine. I believe some of you taking the chemistry, right? So chemistry, I think on 8th, right? Yeah. Okay. 6 students. Oh, 6 students not answering the polling. Not sure who, but I hope you're listening. Based on the polls, now most of you choosing the 10th of June, but 6 students not answering. 5 students now, 10th of June. 5 students not answering. So it's 45% choosing Friday. So I will take this as our schedule. Maybe wait for a few moments. Yeah, this is a dilemma when we have when we conduct online course, because I'm really don't know. I really don't know what you are doing behind of those screens, right? But I don't mind as long as you keep reviewing my materials, my contents. That's okay. 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 I will close the polling. Okay. I hope everyone agree. Okay. Everyone agree. Okay. I will close the pollings. Okay. So 5 students Friday, 1 student Tuesday. All right. Is there any anything that you want to say? Maybe Friday have some schedule conflict with other course? Just let me know. Okay. Okay. If you are feel that Friday is okay, then Friday will be our schedule. Now, before we end our lectures, let me just explain a little bit on what we have in the finals. Okay. So I hope everyone get a clear understanding of what's happening. First is, before the finals, I would like just to say the adjustment for scoring. Okay, so adjustment for scoring. I think as we did last year when we have the online course, uh, because we are having the online course at the second half of our semester. So I will need to adjust our scoring system. Okay? Because I believe offline is, I think, more appropriate and more, it's having more, uh, more percentage, right? More percentage. It's I believe for the fairness in scoring. So probably the final exam at the beginning, this will be a 30%, right? But this will be a little bit lower, so probably around 23 to 25%. Okay. The rest will be distributed to quiz, the quiz offline, okay, the quiz offline, and the midterm, okay, and also a little bit to the other subject like bonus activity, okay, just a little bit, okay, but mostly to the quiz or midterm. So we will have some adjustment. I hope you understand. Okay, you understand and have uh, clear Okay, clear message about this. Okay, so that's the first thing. The second thing is the finals. Okay, so finals, 10th of June, we are using the WebEx. Okay, we will have, because we have 3:30, right, and we have online, right. So I would like you to prepare from 3:20. Okay, 3:20. So please, so before 3:20, I hope you are already go inside the WebEx. Okay, so before 3:20, go to WebEx. The final exam will take around 2.5 hours. Okay, so we will end up around 5:50. Okay, so 5:50 will be the end of the finals. The finals will be consist of 2 sections at most. Okay, first section, so section 1, this was through the quizzes, the platform that you have been doing the quiz lately, right? But this will be live quiz. Okay, so I will guide through some questions randomly, and you need just to answer short questions, expected to be finished on 20 or 25 minutes will be finished. Okay, the second part, section 2, we are going to use another platform. Okay, it's called the Flexi Quiz. This is the platform that I will try for your next quiz. Okay, so this is also going to use your quiz chapter 6 and 7. Okay, and I will announce this on hopefully this weekend. So weekend, maybe Saturday or Sunday. Okay. Now for the finals, the Flexi Quiz has 3 components: part A, B, and C. Part A and B, you need to just to fill in the form. Okay, fill in the form, click the answer, type in the results. If you have some calculations, some questions, you just type in, click the link. Okay, and then part C, aside from fill the form, you need to prepare a paper-based test, paper-based calculations. Okay, so at the end of the finals, you need to send me an email. So send email. Okay. Okay. And one more thing, the Flexi Quiz is heavily depends on your browser. Okay, so please check your browser, clean if you need. If you have a lot of background files, the case files, clean, or please use private browser. Or if you are using Chrome, use the incognito. I think this is a problem when you are using Windows, but if you are using Mac, I don't think it will be a problem. Okay. And if you open many tabs, I hope it doesn't affect your link on the Flexi Quiz, okay, the platform. So if you want to open tabs, do not open on the main computer. Okay, so this is open notes, so you can open your notes. Okay, so open notes, books. Okay, calculators also. Okay, so use every items you have. Okay, maximize your equipment. Okay.
Professor, so you
Yes.
mean the Flexi quiz can crash?
I tried, but it's okay. But I don't want to be having any trouble. So yeah, please be mindful about that. Okay.
Oh, okay.
Okay. So you can prepare notebooks, calculator. If you have more than one gadget, you can use that for other part as well. And I hope, okay, if you want to use using the WebEx and it in your laptop, I think it's still okay. The FlexiQuiz is still okay as long as you don't make your browser crash. Okay, I hope it doesn't happen. Okay, but as I may remember, as I checked and I tried some testings, it's for me it's okay, and for some I checked for other students as well using the same platform. It's still okay, not really having a problem, but I want to make sure it's safe. Okay, it's safe. So I think that's the important thing on the finals, and every part there will be some instructions. Please read carefully before you register. Going into the finals, you will fill the form of your name, student ID, and you will see some message. Please read the message, the whole message. There will be some kind of instruction on how to fill the form, right? Because some parts you need to fill or type in some numbers, right? Yes, Daniel, it will be more secure if you use incognito, okay? Because sometimes I check with other students in other course, if they don't clean their browser, when they type in the answer, it doesn't record in the system, okay? And it is fixed when you are using the incognito. Okay, okay, Daniel. Okay, I think that's all for the finals, and I will have a review next Tuesday morning. So if you want to come to the class, you can come. If you want to skip, if it's okay. If you want to prepare for other finals, because I know that some of you are maybe preparing other finals, so you can manage your schedule, and you can just watch the recording video later. Okay, that's still okay. I just want to have a review on next Tuesday class. Okay. Okay. Any other questions? I think TA is holiday, right? Because it's a dragon boat, right? Is it holiday? Do you remember? I think if the calendar is holiday, then probably it will be holiday. Okay, probably the TA will let you know whether we will have a class or not. But if you want to have a class, I think I can ask the TA to open the class for maybe just a review also, review and practice. I think
Um,
that's still possible. Yeah.
Professor,
Yes.
so now in our class we only have 2 tests left, one quiz and one final. That's all,
Yes.
right?
Yes. Yes.
Okay, thank you.
Yes. Okay. And let me just remind you, if you are having the score maybe in the middle, okay, I hope you still can maximize your scores through the quiz and finals, okay, so that I can analyze later whether I need to give you some homework, okay, or other things, okay. But I think for most of the cases, for most students, I believe up until now, only a few that still having some trouble. But most of you, I believe, if you keep consistent, I believe you'll be okay. Okay, I think that will be my suggestion. Just keep on track, keep study, watch my videos, watch my review, read my notes. Okay, if you have the books, you can prepare the books also. Or if you want to make some like short summary in a paper, in the A4 paper, I think it's also fine. It's easy if you want to have this open notes quiz and finals. You can just look on the paper easily rather than you are opening many books, right? Okay, I think that's my suggestion. Okay, so for the TA class, I will make sure with the TA if he can open the last class for review. I think still okay if you want. Okay, so I think that will be the end of our lectures. Let me give you the QR code if you haven't scanned. So suppose this is the last lectures and you feel that you don't want to come in Tuesday class, that's okay. I would like to say thank you to all of you. Okay, I really appreciate you are able to attend the lectures. Okay, although now we are having an online class, I hope everyone still have the same energy, the same benefits when we are having the offline class. And I wish everyone success, and I hope all of you can pass my course. Okay, I know some of you feel previously when you take my course, the question may be difficult, the quiz difficult, exam difficult, but that is to push you through the system in the Taiwan Tech. Okay, so I hope you can pass through and have a successful career. Okay. Okay, I think that's the end of our lecture. Uh, See you next Tuesday. Oh, thank you, Tam. Thank you. Thank you, Tam.
Yeah, thank you, Professor.
Yeah. Hopefully everyone can enjoy weekend, although we are still in pandemic, and maybe some of you maybe quarantine, right? Okay, so hopefully you can get better health. Okay. So see you everyone. Bye. Yeah. Bye bye.